Hello, this is a video about the Qibec 1-bit 1-instruction transistor CPU that you can see right here. And in this video we'll show how a SR-latch latch can be made out of NAND gates. In the previous video we already showed how NAND gate, NOR gate and inverter could be made out of discrete transistors, and this video is simply an extension of that. We'll show the functionality and the build-up of the SR-latch latch on the whiteboard, and after that demonstrate the behavior on the breadboard by basically hijacking one of Qibec's I/O modules. So let's go. Probably a familiar diagram of a NAND gate is this one. Start with a NAND gate going into a non-inverting output Q. Take another NAND gate going to an inverting output Q overbar, give the block two inputs and make internal connections like this. I'm sorry for the focus artifacts, but it's not a big deal. To make this a bit more easier to understand, maybe let's replace these NAND gates by AND gates followed by inverters, because at least in my head the AND gate makes slightly more sense than a NAND gate. It's more intuitive. So this is exactly the same functionality as before. Now these outputs are labeled Q and Q overbar. That suggests that they are each other's complement. But is that really so? Are they always different? Now let's try to make them the same value and see if that's possible or not. First, let's try to make them both 0. If this output is 0, then the value in front of this inverter would have to be 1. If the output of the AND gate is 1, that means that both of its inputs have to be 1, except one of its inputs, namely the bottommost one, is already 0. So assuming that the outputs can both be 0 simultaneously results in a contradiction. In other words, the outputs can never be 0 simultaneously. So that's that. So let's make them 1 simultaneously. If this output Q is 1, the value in front of this inverter would have to be 0. This is an AND gate. One of the inputs of the AND gate, as you can see, is 1. In order for the output of this AND gate to be 0, the other input has to be 0. If this input would have been 1 as well, the output of the AND gate would have been 1. Right? Now because this circuit is symmetric, you could say that this input is also 0. So in other words, the only situation in which the outputs can have the same value is when the inputs are both 0. Now this is a situation that you don't want. You want the outputs to be each other's complement. So let's avoid a situation where both inputs are 0 at the same time, and you will always have outputs that have a different value. So inputs of 0, 0, avoid. By doing so, these are always different. And that's nice. So let's look at what happens on the input side if one of the outputs Q is 0. We knew that the outputs are always different, so that means that output Q overbar is 1. If this output Q is 0, means the value in front of this inverter is 1. Because this 1 is the output of this AND gate, both inputs to the AND gate would have to be 1. The other input was already 1. Topmost input of the AND gate also has to be 1. If this output value Q overbar is 1, the value in front of this inverter has to be 0. Now this is an AND gate. If one of the inputs to the AND gate is 0, the output will always be 0, regardless of this input. In other words, the bottommost input of this whole block is not relevant anymore. Now the interesting case is, well, for now, if both inputs are 1. So the question is, if we apply a 1 at both inputs, does that force the output to be 0 for Q and 1 for Q overbar? Because the circuit is symmetric, we can also say if this input forces the outputs to be 0 and 1, we can flip it around. Inputs would still be 1, 1, and you would result in a contradiction, namely inputs 1, 1 would also result in outputs 1 and 0, and that's the opposite of what we assumed. In other words, assuming that both outputs of 1, 1 cause the output to be 1, 0 or 0, 1 results in a contradiction. In other words, inputs of 1, 1 result in no change at the output. So remaining as input conditions of 0, 1 and 1, 0. I mean 0, 1 or 1, 0. Let's see what happens if one of the inputs is 0. Because this is an AND gate, if one of the inputs of the AND gate is 0, the output must also be 0. And inverting a 0 results in a 1. In other words, a 0 at the topmost input of the block results in a 1 at the Q output. Right? Likewise, because the circuit is symmetric, a 0 at the bottommost input of the circuit results in a 1 at output Q over bar. We just saw that unless both inputs are 0, you don't want that. The outputs are always each other's complement. Therefore, if this output is 1, this output must be 0. So applying a 0 at the bottommost input causes a 0 at the topmost input. So now we can give names to these inputs, because now the behavior is obvious. If this input would be called R over bar for reset, that would make sense, because applying a 0, that is an active signal, because this is a low active input, and this input would reset the output of the block, and Q is a non-inverted output, so let's say it's the output of the block. Likewise, this input can be named set, S over bar for set, because applying a 0, that is an active signal, because it's a low active input here, sets this output to 1. So now you have a block with memory where you can set the output or reset the output by applying two different signals. Now if you compare this to the NAND gate or the NOR gate or the inverter or AND gate or OR gate or XOR gate, this is a bit different. This is the first block that we talked about, with which has a memory function. It's a class of logic called Sequential Logic. So for Sequential Logic, the output formed by Q and Q over bar doesn't only depend on the current input, but also on the input history or on the current state of the logic. So this is a building block for making things like latches and memory and so on. What we just showed was one way of constructing it out of NAND gates. You can also make this out of NOR gates. It's slightly more convenient within the Qibec CPU to make it out of NAND gates. You can summarize, or actually you can draw something like that, and it means that's the same as the whole picture that we just saw. That's a new logic gate, the SR-latch latch, containing all that we just saw. Now within the Qibec CPU, it's slightly inconvenient to use a SR-latch latch on the breadboard, because there is no I/O module where SR-latch latch is easily accessible. There's always a cloud, so to say, of logic driving a SR-latch latch. In other words, a SR-latch latch is always part of a bigger block. It's not a big deal. If you consider, it's not a big deal, but we have to override these inputs using a wire, for example, by applying a voltage. Now consider that the cloud of logic, so the set of outputs that drive the inputs of the SR-latch latch, have an output impedance. So they drive the inputs of the SR-latch latch with a certain strength. Now we have to override the signal here, so we have to use a small resistor compared to the output impedance of the circuit driving it. That's exactly what we will do on the breadboard. Small resistors, so drive it strong. Now we can see what happens at the output. So let's do that. And yeah, that's a bit small. Let's use that again. Right. For this I use the 8-bit latch module, also shown in another video. It has a number of NAND gates on it. For example, this topmost block in this topmost cell is a NAND gate, and the one next to it is also a NAND gate. And these two NAND gates within this module form a set reset latch, where the leftmost NAND gate, so that's the leftmost cell, the leftmost two transistors form the set NAND gate, and the rightmost NAND gate, so in the cell next to it, forms the reset NAND gate. If you recall the circuit that we just drew, there were two NAND gates. One was basically to set the latch and the other one was to reset it. So let's remember the red wire R for reset. Yeah? Soldered wires here to the input of both NAND gates. So let's put this block, this module, in the test setup. Let's apply power. And let's connect it's not very easy to do. Let's connect the set input to a circuit driving the set input by using push button. Brilliant. This makes for a good video. Right, so now we have a push button to control the input R over bar of the set reset latch. Pushing it will apply a low voltage at the R over bar input. In other words, will activate the R over bar input. In other words, will reset the set reset latch. Actually, we just saw that already. Another input S over bar can be controlled by this push button. Pushing the button will activate the set reset over bar input. In other words, will apply a low voltage. And this was a low active input, so it will activate the input. So the middle LED is the output Q of the set reset latch. For now we ignore the Q over bar input because it's simply the inverse of this output. So if we apply right now the voltage at S over bar and R over bar input are 1 as indicated by the LEDs. So now the set reset latch, the output of the set reset latch doesn't change state. If we activate the set input by pushing this button, we will see that the output changes to a 1 basically. So we set the output. Similarly, we can reset the output by pushing the reset button. So now, unless you push any button, the output doesn't change. So you can set it by pushing, by activating the S over bar input, and you can reset it by activating the R over bar input. That's basically how it works. So yeah, that's all. Now, thanks for watching, and for more information see the Qibec site, that is qibec.org, and if interested also watch the other videos. Let me know what you think, and thanks for watching. So have a nice day and goodbye.